So yeah, like I said, today we're going to change gears a little bit in that we will still be using molar mass once in a while, but we're not necessarily interested in calculating moles. We're talking about something today called percentage composition, all right? And my pen, no, I don't have to pick it up. Percentage composition. And percentage composition is really, it's still an important type of idea, but it's really a historical idea. Years ago, and I'm talking probably 200 years ago, 200 years, where does that get me? Early 1800s, maybe 250 years ago. Yeah, we're not bad, 250 years ago. At the time when kind of the first real chemist was getting started, I've shown you Lavoisier on the book before, right? I've shown you Lavoisier. Have I not talked about Lavoisier? No? Have I shown you this book before? No? All right. So you guys, I'm sure, have heard of Sir Isaac Newton. You heard of Newton before? No? Does anybody know what Newton really is important for? What is Newton really, known for, if you've heard of him? Yep. Yes, law of gravity, very good. That's right. He also had many other laws of motion, if you've taken physics. Sir Isaac Newton took a lot of ideas that were floating around in the mid-1700s, early 1700s, and sat down and thought about all these ideas, like the way things moved. A guy by the name of Galileo was dropping, cannonballs, and some made out of wood and some made out of metal, and studying how they were moving. There was a guy by the name of Kepler that was looking at the planets and the way they were moving. Anyway, he took all these separate ideas and he put them together into one idea, all right, which is essentially the laws of motion. That's three ideas. And that encompassed the law of gravity. And he took physics and put it all together in a nice little package so that all you had to do was learn about Newton's rules and you knew all about these other guys that did all their work. Lavoisier did a similar thing with chemistry. Before Lavoisier, now Lavoisier, he lived a little bit later than Newton, so we're talking late 1700s. Lavoisier did for chemistry what Newton did for physics. He kind of put everything together in one book to kind of give chemists something to focus on. But one of the most important things he did for chemistry was he convinced everyone that we should, as chemists, be weighing everything. All right. So he took a scale, which didn't really exist up to his time. So he really was kind of the first guy to use the scale. Scales would have had to have been made out of little gears and little moving pieces. And before that time, no one had invented anything that had little gears and moving pieces in order to work like a functioning scale. A guy invented kind of a watch just before that, which had all the moving pieces, which helped Lavoisier kind of come up with a scale. He didn't invent the scale, but he used the scale for chemistry. So back in Lavoisier's time, they knew nothing about atoms. They knew nothing about chemical formulas. They knew about elements. They knew about these fundamental parts of matter, things that you couldn't break down into smaller parts, but they didn't know about the atoms themselves. So the question would be, how do you tell one chemical from another? How do you, have a clear colorless liquid and know that it is made of water? And what they did back then is something called a percent composition. They would determine the percentage of weight each element had in that substance. And that's how they would have identified what a substance was. They had laws for this. It was called the law of constant composition, and it resulted in the calculation called percent composition. So this is kind of a historical idea. Let's write down the law of constant composition. There's one more in the middle. Not a fan of, oh, there we go. And chemists like Lavoisier would come up with this idea even before they knew about the formulas. Any given compound has the same composition anywhere in the universe. Water is the same, out of the mighty Sydenham that flows through Alvinston, Ontario, or Lake Huron, all right? chemical, there might be some unknown substances floating around in them. But anyway, the water is going to be the same. The water is the water. Whether you take it from water that's frozen on Mars at the ice caps, or I don't know if there is water. They keep talking about maybe there is some water. But water is water no matter where you go. Here's a theoretical idea. Adding or removing atoms from a compound changes the compound to a completely different substance. Now that's a theoretical idea because it talks about atoms. So atoms of any of a particular compound have the same composition no matter where you are, and adding or removing atoms changes it into a completely different substance. So you can see here water is H2O, but if we have an extra oxygen, we have something called hydrogen peroxide, and that is completely different stuff. This stuff you can drink away, it's not a problem, and this stuff, if it's highly concentrated, you don't want to drink it, all right? And the other example here, carbon dioxide, that gas we can inhale, it wouldn't kill us. You wouldn't want to inhale large amounts of it. It might make you a little dizzy because it's displacing oxygen. But if you inhale carbon monoxide, then that can be very toxic and can lead to death, all right? So those one atom differences have a large difference on the substance themselves. But the thing I'm interested in here is any given compound has the same composition anywhere else in the universe, no matter where you find that particular substance. I don't know where we're at with the note. Okay. So how do we determine the percent composition? Oops. Or what is the percent composition by mass? It is the percentage by mass of each element in a compound. So what percentage of the mass is made up of that particular element? Again, the compound will have the same percentage composition no matter how large or small the sample is. Oh, I was going to write on the board, but I've got to do this on the whiteboard or no one's going to see my writing. So, no matter how much water I'm talking about, whether I have this small amount of water or a large amount of water, the percentage hydrogen and the percentage oxygen will be the same if we're talking about water. Now, don't write this down. Let's talk a little bit about how we calculate percentages so that we don't have to memorize an equation. Just like with my equations I've taught you here, if we could remember the units, we know the equation. If you get a test back, what's the first thing you do? The first thing you do with those numbers that you get. Let's say Jessica gets 8 out of 10. 8 out of 10. What do you do as soon as you get that back? What's that? Calculate it. Tell me how you calculate it. And then what do you do to make it a percentage? Times by 100. We all do that same thing, right? 8 divided by 10 times 100. So 8 divided by 10, 8 divided by 10 times 100. Congratulations, Jessica. You got 80%. I don't know if you're happy with that or not. Let's talk about what those numbers mean. What is this 8 that we're dealing with? What does this 8 really mean? What is the 8 representing? Yep. How many you got right? Correct. So that's how many are correct. This is the number that is correct. And what is the 10 representing? The possible correct answers. Very often we call it the total that you could get. So the absolute total correct that you could get. This is then the total correct. All right? Now, we could be a little picky about this. This percentage is actually telling us the percent correct, because there'd be nothing wrong with calculating a second percentage. We could calculate a second percentage that would be 2 out of 10, all right? 2 out of 10, 20%. What's this 2 representing in this case? How many you didn't get correct or the number wrong the number wrong or incorrect, I'm going to put incorrect. This is still what? The total. And in this case, we could determine the percent incorrect, right? It's still a percentage. What must be true about the percent correct plus the percent incorrect? It has to equal 100 because that takes care of all the possibilities you have in a test, correct or incorrect. You could use that with your parents. They could say, hey, what percentage did you get on that quiz? And let's say you actually only got 2 out of 10 correct. You could say, well, I did pretty good. I got 80%. Wrong. They might not catch that, you see, and then they say, oh, 80%, nice job. Ooh, dodged a bullet on that one. Could you make that sell job? No? Anyway, until they see it. But we don't deal with bonus marks in the physical world. Okay, so this is a percentage. We're going to be doing the exact same percentages in a moment, except we're going to be doing the percentage hydrogen in a substance. It'll just be the mass of the hydrogen over the total mass. How much is it out of the total mass of the substance? So we know how to get percentages, which means we can easily transfer that over to a substance. Now, I'm going to teach you 2 ways to get percentages. The first way comes from the chemical formula. And we can see it there. This particular method is not the method that Lavoisier would use. Take a look at Lavoisier one more time. Because Lavoisier knew nothing about chemical formulas. So we, as chemists in 2015, have the knowledge of theory, which means we can use the crossover method to get formulas, because we know the theory of electrons and atoms and how they become ions and how they can cross over charges. So we are being chemists in 2015 that have the knowledge of the chemical formula. All right? So we're first going to do it from the perspective of 2015. After we do some of these examples, we will calculate the percentage composition from experimental data the way Lavoisier would have done it years ago, because he would have had to do an experiment and figure out how much there was of each of the substances. All right? Okay. If I'm finding the percentage, I always need the total. I need to know what it's out of. How do I find the total mass of carbon dioxide? How would I find the total mass? Yep. Use the molar mass. So we know how to do a molar mass. So let's first get the total. I like to put molar masses off to the right-hand side of the page, because I'm often wanting to do my main calculations on the left-hand side of the page. So I work from the right-hand side of the page. And I don't know if some people need periodic tables. If you need periodic tables, there's some of them up here. Well, I'll just put them out if you want to come up and grab one. And what do we get for the total? 44? Yeah, nice. 44 grams per mole. That's a good thing to think of. Now we're going to determine the percentages of each. There are only 2 atoms in it, so it's kind of like percent correct and percent incorrect. There's only going to be 2 percentages. They're going to have to add up to 100. If I've got a molecule that has 3 atoms in it, I'll have 3 percentages, right? There'll be 3 options. Percentage carbon. Now, don't feel that you have to calculate this separately. Your calculator will do it for you. There are 2 oh, sorry, I got to be careful. Notice how I write carbon first, because it's first, but it's the second number. So be careful with that. I've often made that mistake, because I always want to go to this number, but notice how it's the second one. 12 divided by 44. And if you drop the units at this point, I don't care. And I want your answer to have 3 digits, which means normally it's going to have 1 decimal place. And if you need calculators, I've got some here. So there's some calculators if you want to calculate. So I will take that percentage when you get it. Yep. 27.3. 27.3%. Now, because there are only two of them, you might think, hey, I just have to subtract from 100 to get the rest. But don't do that, because if you've got 3 atoms in it, then you're going to have 3 of them. And if you make a mistake on one, you're going to be in trouble. So calculate them all separately. Now, this is where I was talking about the oxygen. Write it down like this. 16 times 2 divided by 44. Now, your calculator can easily handle that. You just have to press it in the order it is. You don't need brackets. You don't need anything fancy for that. 16 times 2 divided by 44 gives you the answer. And I'll take that number. Conrad, what do you got? 0.7%. And our quick check would be to add those two up. And that gives me 1. So that gives me 3 to that one. That gives me then another 1, 3. That gives me 100 when you check that out. 100%. All right? So what did we do? We found the total for the bottom, and then we simply took the rows of the molar mass to determine its percent composition. If you get the idea, go ahead without me with a pencil. But notice in this one, I will have percent aluminum, percent oxygen, and percent hydrogen. There will be 3 percentages. Don't forget to multiply that 2 through the hydroxide. What did I do? It's a 3. Terrible. And aluminum, one I don't use very often. 27.0. 27.0. Somebody have a total there? What do you say? 78? Is this correct? 78? We got supporters? 78.0 grams per mole. Good to write grams per mole every time you do that for a molar mass. It reminds you of what the units are, which reminds you of what the formula is. Again, a classic mistake I make when I'm in a hurry. I go to the top of my list, but the top of my list is the last element. You got to go to the bottom of your list in the molar mass to get your masses of each of those. I don't need to see the units in the calculation. Again, I'm not worried about what 16 times 3 is. My calculator is going to do that for me. I could have probably wrote just 3 up here, 1 times 3. But for the sake of making it look the same, I'll write 1 times 3. Oh, I don't know. Probably 1 for the formula mass, and then maybe half marks for this, and half marks for that. It's hard to say. I'd like to go 1, 2, 3, 4, likely, maybe. Yeah. Yeah. You got to show me some steps. You got to show me a little bit of work here. What do we got for numbers? Alexis, you got numbers back there? No, you're just hanging out. That calculator is just, resting. What's that first one, Alexis? 34.6? 34.6%. Somebody have the next one? Yep, Conrad. 61.5%. We're getting pretty high. Oh, but hydrogen's not going to be very much. Hydrogen's pretty light. What is the last one? 4.0? 4.0? I don't know if I like 4.0. 3.8? I like that better. And a quick check. That makes, I can't do that math. Does it get to 100? That's okay. I'm going to write 100. The reason it gets us 99.9 is because of the way we're rounding. And I'm sure we're rounding correctly. It's just that sometimes when you round just that one decimal, you lose that little bit. 99.9, good enough. Oops. Back. Now from experimental data. Yeah, unless you're going to like make note of what PowerPoint it's on and just say, you know, see the PowerPoint. It's up to you. But we do need to have the question, right? And unfortunately, it has to describe an experiment, so it's a little wordy. Now you can tell the difference. You can tell that this is experimental because it's describing an experiment that took place. We've got so many grams of sodium, it's reacted with chlorine, and it makes 8.78 grams of sodium chloride or salt. We're going to do an experiment tomorrow where we're going to burn some magnesium to produce magnesium oxide. And we're going to generate numbers like this. In the hypothesis part of your experiment, you're going to come up with the theoretical percent yield from its formula. So you'll need to know what the formula for magnesium oxide is. You can get that from a crossover. And then you'll do the calculations we just did moments ago. Find the total, figure out the percentage magnesium, the percentage oxygen. Then in tomorrow's experiment, we're going to weigh some apparatus, weigh some magnesium. We'll know how much magnesium we have. We're going to cook it in air so that the oxygen can react with it. And then we'll measure the magnesium oxide when we're done. So we'll get numbers kind of like this. We'll know how much we're starting with. In this case, we're starting with sodium. We're going to react it with, in our case, it's going to be oxygen, but in this case, the question is chlorine. And in the end, we get a total mass of the substance at the end, 88.87 grams. Finding the percentage from experiment is easier than finding it from molar mass. We don't need to do as much work. If I want to find the percentage sodium, I simply need, just like on the test, how many I got correct. In this case, the mass of the sodium, that says M with a little Na, subscript Na, mass of the Na, divided by, what goes on the bottom in a percentage? The total, in this case, the mass of the sodium chloride, mass NaCl. And times by 100. And I can't erase, so I'm going to just stick it in there in a different color. I was in a hurry to write the answer down. Times by 100. You get the idea. 3.45 grams of Na was used. In the end, there was 8.78 grams of the total. And times by 100. Then that's going to get us, I'll take a number when you get it. Yep. 39.3%. percentage Cl. I need to know how much Cl there was, mass of NaCl, because again, the total's on the bottom, times 100. And now we need to figure out the mass of the Cl. Relax. You too. How am I going to determine the mass of the chlorine? How am I going to determine the mass of the chlorine? It's Pick on Alexis Day. How am I going to figure that out? Nope, I'm not going to be doing that. That is from the theory, and we are not using theory. Listen to the question. We started with 3.45 grams of sodium. It reacted with chlorine to form 8.78 grams of sodium chloride. How am I going to figure out how much chloride I'm going to subtract? I'm going to subtract the total from the amount of sodium that I started with. You can do that as a separate question. You could do it in one shot. I'm going to write it in here like this. 8.78 minus 3.45. Now, that you've got to put in brackets in your calculator, or you've got to do it separately, because it's a subtraction. If it's a multiplication, you're okay. But if it's a subtraction, it must be done first. Remember the bed myths and all that good stuff? You've got to do your subtraction first. Then divided by the total, 8.78 times 100. So we need that subtraction first. I'm going to just put that in a different color up top. Did anybody do the subtraction all by itself? Have a number? What do you got? 5.33? So 5.33. And do you have a percentage as well? 60.7%. And if we did everything correctly, we should also get 100%. Okay? So from experiment, it's easier. I don't need a molar mass, but I do need to be able to look around and find where all those numbers are. All right, one last example, and then we've got some practice problems. And yes, I know there's so many words. Oh, there's so many words. What's that? Yep. This is more what our experiment is going to look like tomorrow, except instead of heating copper with sulfur, we will be heating magnesium with air that has oxygen in it. We're going to be heating it in a crucible. I don't know if you recall from the beginning of the class, the crucible is a little ceramic jar that has a nice lid on it. I like to think of it like the Dutch oven of the chemistry world, where you put whatever you want to react in there, and then you put the lid on and you heat the heck out of it. Isn't that what you do with the Dutch oven? You put it in the oven and you heat the heck out of it? What's that? Oh, no, I have no knowledge of what you speak of. I've dated myself then on the internet. That's not a surprise. Okay. Now, we're going to start with that crucible and lid, and we're going to weigh it. We're going to put it on a scale. Scale is going to give us a number like that. Actually, our scales only read to 2 decimal places. Then we're going to put the other reactant in it. In this case, it's the copper. For us, it's the magnesium. So we're going to have the crucible and lid with the magnesium. We're going to weigh it. Then we're going to cook the heck out of it. And when the reaction is done, we're going to weigh it again. And we're going to then have crucible, lid, and the copper 2 sulfide. So we need to get our masses out of it. We need to determine the mass of the copper. We need to determine the mass of the probably copper 2 sulfide, CuS. We also need to determine the mass of the sulfur all by itself. We need to do some math that's going to tell us those numbers. So I'm now going to ask on you, what numbers do I have to use and what do I mathematically have to do to figure out how much copper is used in this experiment? Yep. Correct. Second number, crucible lid and copper. Subtract away the crucible and lid, leaves you with the copper. 22.524, 22.524 minus 21.511. And if you've got it, I'll take it. 1.0? No way. 1.013, and we do. We want to keep as many as we can. And that's an important part of experiment. In experiment, when we measure numbers on our scale, we never just kind of round and get rid of any of the numbers, because there's a reason why we bought a scale that will measure that. We bought an expensive scale that will measure it as accurately as possible. What numbers should I subtract to get the copper sulfide? What numbers should I subtract to get the copper sulfide? Bethany, what do you think? The third number? Well, let's think of it this way. Crucible lid copper sulfide. I just want copper sulfide, so I got to get rid of the crucible and lid. Then the first one, that's correct. Yep. 22.776 minus 21.511. And we'll take that number if you get it. What do you got? 1.265 grams. And now I just want the sulfur alone. There's two things that could be done here. Two different ways to calculate this. Both ways are correct, but I need the sulfur by itself. Yep. We want to subtract these two off. Take the copper away from the copper 2 sulfide. You could have also done last number, crucible lid copper sulfide from crucible lid and copper. That just leaves you the sulfide. Both of them will get you the correct answer. It doesn't make any difference. 1.265 minus 1.013. Got a number? 0.252, 0.252 grams. Now we're ready to get the percentages, and unfortunately, I don't have my PowerPoint set up to give me another blank slide, so I'm going to write them all over the empty space, all over the page. You write them down below where it makes sense. So if I want the percentage copper, right, then I need the mass of the copper divided by the total, right? Mass of the copper divided by the total times 100. 1.013 divided by 1.265 times 100. And I'll go way down here, or can I squeeze another one up here? Suppose I could squeeze another one up there. Percentage sulfur. Again, the mass of the sulfur over the total. Mass of the sulfur down at the bottom over the total. It's always the mass of what we're interested in over the total. The mass of what we're interested in over the total. That's just like your tests. Just think like you're marking a test, except you're getting sulfur instead of correct or incorrect. I don't know. Does that make any sense? 0.252. Oh, I'm really squeezing it in there, eh? 1.265 times 100. We'll take those. We'll see if they total up to 100. Conrad, you got numbers? 80.1%. And keep going. 19.9% equals 100%. That is the correct percent composition. Okay. So, why are we doing this? Percent composition is still a useful tool. There are pieces of equipment that are used in things like, well, I would say forensics, just because that's the cool place in which it's used. But it's used anywhere that you want to identify a substance. You may have seen on shows, and like years ago it was CSI, but I don't know, are there any of those types of shows still on? Yeah. CSI, where they would take a sample and then you'd see them inject something into a machine, and then they wait around for a while, and then it spits out a printout. Usually it happens way too fast on the show. It actually probably takes hours and hours for the machine to do its thing. But what the machine is doing is it's taking the substance, it might be burning it, it might be separating it out with something called a chromatography method. It might be separating the masses out using something called a mass spectrometer. But in the end, it will spit out a percent composition, and that will give chemists an idea of what the substance is. All right, so still a very useful thing. Okay, so that's the end of my PowerPoint, and I'm going to guide you to, the Google Classroom. Practice problems. The answers are right down below so that when you do them, you can check them. All right, and that's what we're doing for the rest. You can work on those problems. I'm going to escape out of my video. Let it do its